As a set of discoveries and devices, science has mastered nature. But it has been able to do so only because its values, which derive from its method, have formed those who practice it into a living, stable, and incorruptible society. Here is a community where everyone has been free to enter, to speak his mind, to be heard and contradicted. And it has outlasted the empires of Louis XIV and the Kaiser. Napoleon was angry when the institute he had founded awarded his first scientific prize to Humphrey Davy. For this was in 1807, when France was at war with England. Science survived then and since, because it is less brittle than the rage of tyrants. This is a stability which no dogmatic society can have. There is today almost no scientific theory which was held when, say, the Industrial Revolution began about 1760. Most often, today's theories flatly contradict those of 1760. Many contradict those of 1900. In cosmology, in quantum mechanics, in genetics, in the social sciences, who now holds the beliefs that seemed firm 50 years ago? Yet the Society of Scientists has survived these changes without a revolution and honors the men whose beliefs it no longer shares. No one has been shot or exiled or convicted of perjury. No one has recanted abjectly at a trial before his colleagues. The whole structure of science has been changed, and no one has been either disgraced or deposed. Through all the changes of science, the Society of Scientists is flexible and single-minded together and evolves and writes itself. In the language of science, it is a stable society.
Jacob Bernowski, Science and Human Values. Before the Enlightenment era of the 17th and 18th centuries, people thought everything important and knowable was already known, enshrined in the unquestionable authority of ancient writings, institutions, and cultural traditions. While these all had bits of useful knowledge, that knowledge was bound up with many falsehoods. But because they were enforced as dogmas, much like the memes of ancient Sparta, the knowledge contained in them could not be improved upon, and their many falsehoods carried over from father to son. So they believed that knowledge came from authorities that actually knew very little, and therefore progress depended on learning how to reject the authority of scholars, priests, sacred texts, traditions, and rulers. This rejection of authority was a necessary ingredient for the scientific revolution. Take no one's word for it was the motto of the Royal Society.
Ancient ways of thinking where creativity was used to suppress change rather than to cause change.
A necessary ingredient, yes, but not a sufficient one. After all, authorities had been rejected before, many times, and that rarely, if ever, caused anything like the scientific revolution. During the scientific revolution, which was but one aspect of the Enlightenment period, people believed that what distinguished science was the idea that we derived knowledge from our senses. But this doctrine, empiricism, can't be true. For one, it rules itself out, as we cannot possibly derive knowledge about empiricism itself from the senses. Besides that, the eye only detects light, and the brain only detects nerve impulses, and yet most of the world isn't made of light, and hardly any of the world is made of nerve impulses. So none of our perceptions reveal to us the world as it truly is. Our senses are woefully incomplete, error-prone, and indirect. Finally, scientific theories explain the seen in terms of the unseen. And the unseen, you have to admit, doesn't come to us through the senses. We don't see those nuclear reactions in stars. We don't see the origin of species. We don't see the curvature of space-time and abstract entities like heat and energy. So empiricism can't be how science works, nor how we know about these things. And yet, we do know about them. How? Empiricism replaced the old authorities of knowledge with the authority of the senses. Because of the senses' supreme role in this new scheme, empiricists sought to justify how knowledge of what has not been experienced could possibly be derived from what has been experienced. The conventional wisdom was that the key is repetition. If one repeatedly has similar experiences under similar circumstances, then one would be justified in extrapolating or generalizing that pattern and predicting that it would continue. This method of extrapolating the future from repeated experiences, called induction, is best seen in the classic example of the rising sun. The inductivist sees that the sun rises each morning, and so extrapolates that it will rise tomorrow morning as well. As the days go by, the sun continues to rise each dawn without fail, and the inductivist's confidence in his theory only increases. Except that modern science tells us that the sun will not, in fact, rise each morning until the end of time. Stars are not immortal. What was the inductivist missing? Bertrand Russell illustrated the shortcomings of induction in his story of the chicken. The chicken noticed that the farmer came every day to feed it. It predicted that the farmer would continue to bring food every day. Inductivists think that the chicken had extrapolated its observations into a theory, and that each feeding event justified this theory even further. Then one day, the farmer came and wrung the chicken's neck. So much for extrapolating the future from the past. The truth is that inductive extrapolation of observations to form new theories isn't even possible. Though they wouldn't admit it, inductivists always guess a theory or explanation first, and then fit their so-called extrapolation into that framework. For example, in order to induce its false prediction, Russell's chicken must first have had in mind a false explanation of the farmer's behavior. Perhaps it guessed that the farmer harbored benevolent feelings towards chickens. Had it guessed a different explanation, that the farmer was trying to fatten the chickens up for slaughter, for instance, it would have extrapolated the farmer's behavior differently. Also suppose that after the chicken's first 100 days of receiving food every day, the farmer suddenly doubled the size of all the meals. Would the chicken then extrapolate that all future meals would be twice the size for the rest of eternity? Or would the chicken extrapolate that its meals would only be twice the original size for the next 100 days, only to revert to their original size after that? The chicken will choose to extrapolate according to whatever theory he has about why the meals changed in size in the first place. In other words, the chicken's prediction about what will happen follows from its explanation about what's going on.
A lot of the interesting things in life are explaining the seen in terms of the unseen, which means that very often things will happen that are nonlinear, that suddenly there's emergent properties or there's a nonlinearity or kink in the curve where something unexpected happens. How did that happen? You're boiling water, it goes 98 degrees, 99 degrees, getting hotter and hotter and hotter, and 100 degrees, oh, it's really hot, and then stays at 100. What's going on? Well, it's turning into steam, but the water's not getting any hotter than 100. The steam is hotter than the water. You're going to burn yourself in the steam, or you can drive an engine with more power with the steam than you could with just the water. So clearly something here has happened that you need to explain, and life is full of these.
This is true in general. Science isn't primarily about making predictions, but rather explanations. Predictions are merely downstream from good explanations, and we use predictions to test those explanations. In other words, explanations are primary, and checking their predictions against reality is one way that we can test our explanations. It is here that senses do play a role. They're not the source of our theories, as the empiricists taught, but are instead a crucial part of how we compare our theories as predictions with reality. Whether that is a laboratory experiment, think of the particle collider at CERN, or an exercise in data gathering, such as when astronomers peered through their telescopes. And even when we do employ our senses, our connection to reality is always, as Karl Popper said, theory-laden. When you look up at the night sky, you see cold, dim, tiny pinpricks of light we call stars. That image couldn't be further from the truth. In reality, stars are extremely hot, bright, and large. But how do we know this about stars, when no one has ever gone anywhere near one of them? As I said earlier, scientific theories explain the seen in terms of the unseen. Consider dinosaurs. No one has ever seen a dinosaur. We explain the seen, the evidence of fossils, in terms of the unseen, a story about what this thing was that walked the earth tens or hundreds of millions of years ago. Scientific theories are explanations, assertions about what is out there and how it behaves. The origin of all human knowledge is not sensory data, as the empiricists claim, nor is it an extrapolation of the future from the past bold guesses, as the inductivists say. Our knowledge consists of bold, creative guesses, never authoritative, always subject to improvement. Because theories are the result of guesswork, we should only ever adopt them tentatively. All people make mistakes. We are fallible. So we should expect even our best knowledge to contain mistakes in addition to truth. There are no authoritative sources of knowledge, nor is there a way to establish a theory's truth or likelihood. We should always expect to find more problems with our theories and even better explanations to supersede our most cherished ideas. As long as we continue to look for problems, this process can continue forever. Science and philosophy are both unending quests, and there is no bound on the progress we can make. During the Enlightenment, the West figured out how to create an unending stream of knowledge. Indeed, the Enlightenment may be defined as the period in which people finally figured out the necessary ingredients to create a never-ending, ever-expanding, ever-improving knowledge stream. For the first time in history, people embraced the radical notion that knowledge could be increased and improved. This optimistic stance, rejected by their ancestors, became the motivation for a new intellectual tradition, a tradition of criticism. Much like the ancient Athenians, Enlightenment thinkers understood that it is through criticism that we may refine our ideas and determine which idea is best amongst several competing theories. The result was explosive. The West became one of the most dynamic societies in history, rapidly discarding memes that suppressed creativity in favor of those that encouraged it. So the Enlightenment brought more than just new ideas. It changed how we think about ideas themselves. Enlightenment thinkers realized that explanations of the world ought to be, as David Deutsch says, hard to vary. That is, no parts of an explanation should be arbitrary. Newton's theory of gravitation wasn't widely accepted only because experiments corroborated its predictions, but also because it was a hard-to-vary theory. Gravity, force, mass, acceleration. Each concept played a vital, interconnected role in the grand play that Newton had created. Change any single component, and the entire explanatory edifice collapsed like a house of cards. Finally, the West gradually developed institutions such as hubs for scientific research, as well as networks connecting scientists, patrons, and writers that protected the capacity of people to criticize ideas without fear of oppression or violence. The Republic of Letters, for instance, spontaneously emerged sometime in the 1500s and served as a vital precursor to Enlightenment-era scientific institutions such as the Royal Society, which was, in turn, founded in 1660. As law professor Michael J. Madison writes, across Europe and eventually in North America and Southeast Asia, thousands of experimentalists, observationalists, natural philosophers, and collectors, men of letters, philosophers, savants, a self-identified intellectual aristocracy operating outside the formal boundaries of nation, state, and church, documented their studies in letters and distributed them in far-flung correspondence networks, conducted not only through letters, but also through books, pamphlets, and other printed publications. The product of this intellectual exchange was a large, distributed, self-governing collective of early scientists and philosophers, bound to one another informally, but normatively, by a well-understood, if imperfectly enforced, system of rules and guidelines. Written correspondence was linked to in-person visits and conversation, and eventually to the formation of early learned societies, scientific academies, salons, and scholarly journals. During the height of the Enlightenment, the West roared not only with dynamism, but with optimism. People thought that progress was both possible and desirable. Perhaps no group embodied this spirit better than the Lunar Society of Birmingham. Meeting monthly by the light of the full moon, this diverse group of innovators came together with a common goal: to harness science and technology for the betterment of humanity. The Lunar Society boasted, as Professor Bridget Kapler writes, James Watt, the designer of the great steam engine, Erasmus Darwin, a poet, innovator, physician, and botanist who published his own theory of evolution and developed a mechanical steering system that would later be used on Henry Ford's Model T. Joseph Priestley, a rebellious Unitarian cleric and scientist who first isolated oxygen and developed carbon dioxide. Josiah Wedgwood, fondly called the father of English pottery, who was dedicated to improving his manufacturing techniques and seeking better means to complete his work. William Herschel, the astronomer who discovered Uranus. John Smeaton, a civil engineer and mathematician who built canals and the Eddystone Lighthouse to withstand the pounding of the waves through the use of hydraulic lime. James Keir, the chemist who made an affordable soap for the masses. Richard Lovell Edgeworth, a keen inventor and educator. William Murdoch, the inventor of the gaslight. William Small, a mathematician and philosopher. William Withering, a physician and botanist who discovered the heart disease could be treated with digitalis from the foxglove plant. And Thomas Beddoes, a country physician that recorded many cures and expanded the frontiers of medicine. Approximately a dozen men at its height, the Lunar Society of Birmingham unified themselves as a pioneering collaborative with the goal to weigh and consider the conglomeration of science and social change. Many of the institutions and traditions that blossomed during the Enlightenment survive to this day, albeit in more modern forms. We are fortunate today to still have things like the scientific community and the scientific tradition, and we tend to take these for granted. For example, if a professor in a seminar were to respond to a question by saying, "You're not allowed to ask that, just trust me, I'm the professor," he would be laughed at. Although there are many areas of life where such a response might not be met with laughter, science is one domain where it is taken for granted that criticism is part of the culture. The Enlightenment is the moment at which explanatory knowledge took center stage as the most important determinant of physical events for everyone in its vicinity. Its sphere of influence has only expanded since then, and could, in principle, swallow the entire cosmos whole in due time. But we had better remember that what we are attempting, the sustained creation of explanatory knowledge, has never worked before. We were once the victims and enforcers of a horribly static society. We now have a duty, and it is a wonderful duty, to accept our new role as active agents of progress in our post-Enlightenment society and of the universe at large.